Hey guys, welcome back. My name is Mr. Kim, and today I'm going over the June 2022 Chemistry Regents FRQ section. So let's get started. Number 51. Okay, two naturally occurring isotopes of lithium are Li6 and Li7. Table below shows some blah, blah, blah. Okay, state the number of electrons on an atom at Li7. Now, these are atoms, right? So atoms of lithium. So what do we need to do? We need to look at the atomic mass number. I'm sorry, atomic number, right? So let's go. So if you look at lithium, that should be what, in the first group? All right. So going to the first group, we got 3 for atomic number. See that? So therefore the answer is 3 electrons. So 3 is your answer. Let's go to 52. Compare the energy of an electron in the first shell of lithium to energy of the second shell. So what do we know? The first shell is, or the closest to the nucleus, is always the lower, right? So the first shell has lower energy than the second shell, or vice versa. Okay, 53. Show numerical setup. Okay, once again, numerical setup for calculating the atomic mass of the element lithium. All right. So what do we got? We got this one and this one, right? So essentially, we've done this so many times that this should be very easy at this point, right? So it's going to take the atomic mass, 6.015 times the abundance as a decimal, 0.0759 plus the mass number is 7.016 times its percentage in decimal is 0.9241. So this is the answer to 53. All right, let's go to 54. 54. State the general trend from the atomic radius of the first 7 elements of period 3 when considered from order from left to right. All right, so we're looking at period 3, which means we're going this way, right? And look at the radius. Now, you don't have to know anything here. They're just asking you if you see the trend, and trend obviously is what? It's going down, right? So going from left to right. So, and let's just verify that it is sodium to argon. So it is going left to right. So the trend is getting smaller. The atomic radius or radii gets smaller from left to right across the period. Okay, let's go to 55. State in terms of valence electrons, which means we have to use this word, why aluminum and sulfur have different chemical properties. Now, this has nothing to do with aluminum and sulfur, right? It just tells you why 2 different atoms have different chemical properties, right? So you would say aluminum and sulfur. What do we know about their valence electrons, right? Are they in the same family? They're not, right? Because aluminum is a metal and sulfur is a nonmetal. Have different numbers. Numbers of valence electrons. Okay. You could actually also write the number of valence electrons. You can go look up aluminum, whose valence electron is what? 3, right? Aluminum has 3 and sulfur has 6. So you could actually write that as well if you want to. Identify the element in period 3 that reacts with oxygen to form an ionic compound represented by X and X2O. X2O looks a lot like H2O, doesn't it, right? And what do we know? In that case, H is a +1 ion, right? So who is the element in period 3 that reacts with oxygen to form that? It would be sodium, because remember, everybody in the first, right, column is +1. So they want the element, so you write sodium. 57. Lithium, beryllium, boron, fluorine are 4 elements in period 2 in the periodic table. Once again, we're going in a period, right? State in terms of electrons why the radius of Be2 plus ion is smaller than the radius of a Be atom. Well, think about this. Be2 plus ion means what? It's protons, right? Beryllium is right here, and it's got 4, right? It's got 4 protons, right? So it's got 4 protons, and this also has 4 protons, but it has how many electrons, right? It has 2 electrons, and this has 4 electrons, right? So what do we know? We know that in the beryllium cation, or all cation for that matter, have less number of electrons to number of protons in the nucleus, right? So the answer would be that Be2 plus, right, has 4 protons, while only 2 electrons. So the electrons in Be2 plus are held tighter, right? Hence you get the smaller radii. Okay. 58. Draw a loose electron diagram for an atom of boron. Oh, please. I mean, you're pros at this, right? Boron is what? 5 electrons. So let's go. Oh, actually, that's not true. Let's see. Because Lewis diagram means what? You're drawing the valence electrons, right? So boron has a, oh, that's 3, right? 3 valence electrons. So to draw boron, it would be drawn like this. B with first 2 electrons on top and 1 on the side. Now, you could also write it. It doesn't really matter. As far as Regents concerned, they don't care. As long as you write it, it doesn't matter. These are all correct. What is not correct is doing this. They're not going to give you credit for that, right? 59. Oh, it's organic. Is it though? Incomplete equation below represent reaction between 2 butene and hydrogen in the presence of catalyst producing 1 compound X. All right, so it is organic. Explain terms and molecular formulas and structural formulas why 1 butene is an isomer of 2 butene. Now, if you think about this, this is also, again, even though I said it's organic, it's not really organic. They just want to know, right? Definition of isomer. Isomer, once again, is what? Same chemical formula, but different shape or different structure, right? So because it's the same chemical formula, what do you expect? You expect the molecular formula to be the same, right? Right? So both have the same molecular formula. What just happened? But different structural formula. Okay, let's go to 60. Draw a structural formula for the missing product X in the equation. What are we looking at? We're looking at this, right? But what's happening here? We got hydrogens coming in. And remember what we said in class. When hydrogens come in, what happens? It's either going to be double bond or attached to hydrogen. So what is probably going to happen is what? The 2 hydrogens are going to come in here and here, right? So that's 4 carbon. So it's essentially going to take this alkene and turn it into an alkane, which is all single bonds, right? So let's go ahead and draw that. So it's going to be 4, 1, 2, 3, 4, and it's an alkane. So you're going to draw it like this. Now, leaving it like this is perfectly fine. But like I said to you guys in my class, try to just draw in the hydrogen because, like I said, sometimes kids screw up and then, right? Let's not take shortcuts, right? There it is. 61. In a titration using a pH meter, 16 milliliters, that's a volume, that's a base, so I'm going to put VB, and that's MB already. Exactly neutralize a 24 milliliter sample of HCl, that's VA, in a flask. Can you tell what we're going to be asked to do later? Right? During this laboratory activity, okay, so it's safety equipment, blah, blah, blah. State the number of sig figs used to express the volume of the HCl. All right, so let's go take a look. It's 24.0, right? What do we know about the trailing zero? Remember the pickup line, right? Baby, I'm a trailing zero and you are the, what in my life? Right, the decimal, right? So if you're a trailing zero, right, you need a decimal in your life because the decimal makes you significant. So this would have 3 sig figs, right? So let's go. It's going to be 3 sig figs. Okay. Those of you who are not from my class who are tuning in, because apparently 50% of the people viewing is actually from YouTube. If you don't know what that pickup line was, that's something I use in my class. Maybe I'll make a video on that in future. Number 62, identify the negative ion of NaOH used in the titration. Okay, so what is it? It's a hydroxide, right? So you're going to write down hydroxide. Right. If you, I can't really imagine somebody messing this up unless you dissociate the OH. But remember, it's a polyatomic. Polyatomics don't fall apart because they're covalently bonded, but they act like an ion. Number 63. Compare the number of moles of hydrogen ions, number of moles of hydroxide ions in a titration mixture when a HCl is exactly neutralized. Hey guys, what does that mean? That means acid, base is what? Same, same. What does that mean? Right? That means the number of moles of the OH minus and H3O, you don't have to write this part, are the same, right? Because you're neutralized, right? Okay, number 64, complete the equation in this booklet for neutralization by writing the formula for each product. Okay, so let's go. Hey, so they actually made this a little bit tougher this time, right? Because what do we know? It's going to be about salt and what? What do you think? That's right, it's salt and water, right? What's the other part? The other part is this with that, right? So that's going to be literally sodium chloride like that, right? And if you double check, we are already balanced, so we're good to go. 65. I don't even have to ask about 65. We know what's going on, right? Determine the molarity of the HCl. So that's Ma, right? So it's MAVA equals MAVUB. And if you don't know, if you go to the back of the reference table, the equation is right here. But like I said, remember, I told you guys, you should try to memorize that, right? Right here. There it is, right? All right, so let me see. MA is our unknown. VA is what? Come on. VA is 24.0 milliliter, right? MB, VB, right? And these are respectively 16 milliliters and 0.18 molar, right? 0.18 molar and 16.0 milliliters, okay? So plugging this in, what do we get? We get MA is equal to MB VB divided by VA, and we get 16.0, oh, sorry, that's the wrong, it doesn't really matter, but I put it out of order, didn't I? It would be 0.18 molar times 16.0 milliliters all over VA, which is 24.0 milliliters. Now, do we need a calculator to solve it? I guess it's helpful, right? But we could try to do this without it. 4 goes into 16 4 times. And 4 goes into 24 6 times, right? And then what happens? 6 goes into 6 once, 6 goes into 18. That many number times, which comes out to, what is the value? 0.12, okay? So that's 0.12 is our answer. All right, let's go on to 66. 66. Okay, an average person on board of International Space Station requires 840 grams of oxygen, that's O2, per day. To produce oxygen needed in this, it said water undergoes electrolysis reaction. Oxygen produced is vented into the ISS cabin, and the hydrogen is vented into outer space. That's not true. I think they use it to for burning as a rocket fuel. The reaction is represented by the balance equation below. All right, so you have that, right? Now what? Some gas in the ISS must be removed from the air and the astronauts can breathe. Carbon dioxide can be removed using solid lithium hydroxide. Show numerical setup for calculating the number of moles of oxygen gas required for average person per day. All right, so what do we know? We got average person requires 840 grams of O2 per day, right? They want moles of O2, right? So what happened? We want moles of O2, so we know that it's grams per mole like this, and it's given to us, right? 32 grams per 1 mole, and that's given to us right here, right? And therefore, let's see if Mr. Kim has the value. Maybe, maybe not. Oh, no. Hey, look at me, right? I almost screwed that up, right? Why? They want the numerical setup. So essentially, you want to show the setup. It's 840 grams of O2 times 32 grams per 1 mole. Okay, this is your answer. State the change in oxidation number of oxygen during the electrolysis reaction. Oh, so easy, right? Because what's the easiest one to do here, guys? Right, the one on the right? You know that's a 0 because it's diatomic, right? Rule number 1 from my class. What about here? Oxygen is almost always -2, and we're done, right? So therefore, it's going to be -2 to 0. Cannot get any simpler. Determine the number of moles of oxygen vented into cabin when 120 moles of water undergo electrolysis. Okay, so it's 120 moles, right? 120 moles of H2O, right? And then you want to go 2 moles of O2. So if you go up here, what do we got? We got these two values right here, right? So we got 2 for water, and you got 1 for oxygen. So it's 2 moles of H2O to 1 mole of O2. That's the coefficient ratio. And essentially, what are we doing? We're just dividing by 2, so it's going to be 60. And it's going to be, how many sig figs? It's going to be 2 sig figs, right? Because it's 120, which is 2 sig figs. So the answer is 60 moles. Let's go to 69. 69. Determine the percent composition by mass of hydrogen in water. Come on, guys. That's easy, right? It's going to be mass of oxygen over mass of H2O times 100, right? What's mass of oxygen? Is going to be 15.9994 grams per mole divided by what's H2O? H2O is going to be 18, right? Give or take. I'm just going to put 18. I was going to be very accurate, but I don't think it's necessary, right? So it's going to be 16 divided by 18, right? Do I have that value? This is number 70. I don't think I do. 69. 70. I don't understand what's going on. Is this the right test? It looks it. All right, so I'm gonna have to plot my calculator and try to do it separately. There we go. So 16. Oh, sorry, I'm waiting for a calculator to turn on. Right, it's gonna be 88.9%. Okay. 88.9%. Let me just make sure I did this correctly. Oh, guys, percent composition by mass of hydrogen. What am I doing with oxygen, right? So that's wrong, right? What's hydrogen? It's the mass of H2, right? Or not H2, but two H's, right? Because there's two H's in water. So the correct way is actually what? 2/18 times 100, right? Right, 2 divided by 18, that gives me 11.1%. So that's the correct answer, is 11.1%. I could have actually taken 100 and subtracted 88.9. I would have gotten the same thing. All right, number 70. It looks like we're going to balance this, right? Balanced equation, you guys, the booklet, so smallest whole number coefficients. Let's tackle this, right? So what do we got? We got, we're going to leave the oxygens and hydrogens till the end, right? So we got lithium. We got 2 on the right, 2 on the left. So I'm going to put 2 right here. What does that change us? Now, carbon, it's 1 on the left and right. So I'm guessing it's actually correct. So let's take a look at the left side. Left side, you got 2 hydrogens on the left side. Let's go to the right side. I also see 2 hydrogens. Let's do the oxygens. You got 2 plus 2, which is 4 for oxygen. And on the right side, you got 3 plus 1, which is 4. So we are correct. You can leave it this way, or you can actually do this. It doesn't matter. They're correct both ways. 71. Parts per million. This is pretty easy, right? Because where do you get the equation for parts per million? It's right near the parts per percent, right? But like I said, you should memorize these, right? It's super easy. It's right here, right? It's mass of the solute over the solution, right? So let's go. Who is the? This is the water, right? And this is the solute, right? So it's going to be what? 0.00075 grams over the solution, which would be the sum of the both, right? It's 150 plus this, so it's going to be 0.00075. Now, that's not going to make a huge difference, except, right? You get something like this, right? So now, you can punch this in a calculator, right? Or what you could do is, if I do the top first, right? I know that I'm going to move the decimal place on the top 6 places to the right because I'm multiplying by million. So it's going to be 1, 2, 3, 4, 5, 6. So it's going to be 750 divided by 150 and change, right? And what does that come out to? That's going to be what? Zeros cancel out, 75 over 15, right? 15 goes into 75 how many times? Goes into 5 times, right? Or you can just take a calculator. If you punch it in, you'll get the magical number 5 as well. Okay, so it's going to be 5 parts per million or 5.0. Yeah, I don't think it matters if you put 5 or 5.0. Using the key in your answer booklet, draw at least 2 water molecules in a box showing the orientation of each water molecule towards the calcium 2 plus ion. Now remember, this is cation. What do you know about water? We know the water that the oxygen side is slightly negative and the hydrogen side is slightly positive, right? So that's it. That's what they want to know. So let's go over here, right? Did we do number 72? Oh, I'm sorry, we didn't do number 72. Let's go do number 72. State in terms of aqueous ions why the tap water can conduct electrical current. Well, what do we know in class? By definition, right? Salt water can conduct because tap water must contain mobile aqueous ions, right? Because remember, if you have freely moving ions, you can conduct electricity because the electrons are carried on the backs of these. All right, back to 73. We're drawing the water, right? So how do we draw the water? Well, we know that the chin part of Mickey Mouse, or the face of the Mickey Mouse, is going to be pointing in because that's the part that is more negative, right? Same thing over here. So you can draw another one over here like this because they said draw at least how many? 2 water molecules. So we're done. Let's go to 74. 3% hydrogen peroxide solution, H2O2, is commonly used as disinfectant. Hydrogen sulfide decomposes as below. Hold on a second. Hey, sorry about that. There was a phone call. Never get phone calls. That was kind of weird. All right, so let's go back to this, right? It says here, state evidence from the equation that the reaction is exothermic, right? Well, hello. Exothermic means what? Heat is on the product side, and there it is, right? So that's literally what you're going to write, right? You're going to write that heat is on the product side, or what else can you write? I'm going to use different colors so you know that it's not part of the same answer. Or conversely, you could actually just say the definition of exothermic reaction. Just say heat is released, right? So either one of these answers would be considered correct. Continuing on words. Explain in terms of substances. Now, again, just be careful. When they say explain in terms of, you must use those words. Why the reaction is decomposition reaction? Well, hello, let's take a look. It's got how many substances on the left? 2 substances. I'm sorry. It's going from one substance, which is all H2O2, to 2 substances, right? So, right, H2O and O2. So that's literally what you write. You're going to write reaction goes from one substance, there's that word, to 2 substances. All right, let's go to 76. State how increasing the temperature of H2O2 affects the rate of reaction. Now be careful though, right? Now normally you might want to say that, hey, increasing heat and yada yada, maybe the reaction is going to go forwards or backwards. But you have to be careful here because in this case, the arrow, look at this, it only goes in one direction, right? So if the arrow was going in both directions, adding heat will drive it backwards because, you know, you're adding products. But in this case, it only goes in the forward direction, right? So the answer here is that when you add heat to a chemical reaction that's unidirectional or single in one direction, it only makes the reaction go, what, faster or slower? What do you think? That's right, makes it go faster. So you would say heat raises the reaction rate, okay? All right, next, 77. On the potential energy diagram, draw a double-headed arrow to indicate the interval that represents heat of reaction. Well, what is heat of reaction? You got to really figure that out first. It's the difference in heat energy between the reactants and products, right? So that's the heat of reactants. So where is that here? So reactant starts here and products is over here. So the difference would be found right here. Okay. You can draw it over there or you can draw it over here. It doesn't matter. 78. Hey, this is a what? It's a voltaic cell. Hey, they even told you, right? So identify the subatomic particle that flow through the wire as the cell operates. Sorry about that. Another distraction. Somebody just popped their head in, right? I had to pause the video. All right, subatomic particle that flows through the wire, folks, right? What's the only thing goes through the wire? It's electrons, right? Right? So the answer here is 78 electrons. Okay. All right, 79. Compare the number of electrons lost and number of electrons gained during the reaction in operating cell. Well, this is just definition of redox, right? Because remember, whoever loses electrons, the other has to gain. So the number of electrons, right, of electrons, right? You can add lost and gained, but it doesn't matter, are the same. Okay. Oh, that's bad. Sorry about that. I'm trying to speed up because I got people calling me and coming in. I don't know why. Nobody ever comes to visit me in my classroom. State the form of energy that is converted to electrical energy in the operating cell. Dude, there's only two answers, right? One is chemical to electrical in a case of voltaic, and in a electrolytic, it's using electrical energy to drive a non-spontaneous chemical reaction. So says it's electrical. So what's the answer, kids? What do you think? That's right. It's chemical energy. 81. Write a balanced equation for the half reaction that occurs in the copper half cell when the cell operates. All right, so what are we looking at? We're looking at this, and we're looking at that. So it's going to go from copper 2 plus to copper solid. And what do we know? It's going from +2 to 0 on the right side. So you know to balance it, you have to do that. Or the other thing is, you know that copper is actually reducing because it's going from aqueous to solid, right? So that's what we're going to write down here. Copper 2 plus, and that's our aqueous ion, plus 2 electrons goes to copper solid. Let's go to 82. Identify the metal from table J that is more easily oxidized than magnesium. Easily oxidized means it's higher in the table J, right? So let's go take a look. Have you noticed how little we actually use the reference table, right? It's not nice when you memorize some stuff. All right, here we go. So go to J. Here we are. We got magnesium. Where's magnesium? Magnesium is right here. So who's the answer? Answer is, be careful, right? Now it says one metal, right? Let's take a look. It's any of these, right? If you take a look, in fact, they're all metals. So it's any of these, right, is a correct answer, right? I'm going to go with lithium because it's like mad high, right? So lithium, except you can write any one of those that's above magnesium. 83. All right, that's it. Final stretch. Element 117, UU, has been synthesized and has at least two isotopes, UUS 293 and 294. Atoms of 293 can be made by bombarding BK249 with calcium 48 in a reaction represented by the nuclear equation below. The BK249 has a half-life of 320 days, decayed by beta emission and also emitting gamma rays. Determine the fraction of BK249 that remains unchanged after 960 days. So we want to know 960 days is how many half-life events. And we know that it's what? It's 320 days per one half-life, right? So the and then we double check. It's not asking for the numerical setup, so we got to calculate it. So let's just do it here. It's 960 days, right? Times, you want to get rid of days, and we'll figure out how many half-lives, right? So it says that it's 320 days for one half-life. And most of the time in FRQs, it's going to be a whole number. And in this case, what is it? Guys, it's 96 over 32, which is what? 3 half-lives, right? Now, we're not done though, because what does that mean? That means we're going to go half of a half of a half. So we're going to start with what? We're going to start with a 1, and then we're going to undergo 1 half-life, which means we're going to be left with how many? That's right. We're going to get left with half. 1 more half-life means you're going to be taking half of a half, which is a quarter. And then finally, the third half-life is going to give us 1/8. So our answer is 1/8. Okay. State in terms of both protons and neutrons why UUS-293, UUS-294 are isotopes of the same element. Again, definition of isotope is what? That the number of protons, right? Protons the same. And what do we know about neutrons? Neutrons are different, right? So let's go take a look. And sure enough, that's literally what we're going to write. We're going to write same here, and we're going to write different. Now, if you really wanted to, right, you can actually go look them up, right, and then write the numbers down. I think if you look it up, what do we get? I think for the number of protons, I think it's 117 or something like that, right? So you can write it if you want to. You don't have to write it. It's completely unnecessary, right? And then the neutrons is what? You have two different numbers, right? It's 293 minus 117 and 294 minus 117, right? So I wouldn't really go about doing that. Just do the definition. All right, final. Complete the nuclear equation in your answer booklet for the alpha decay of UUS by writing a notation. All right, so let's take a look. This is super easy, right? We are good with this, right? Don't screw this up, right? Look, it's 117 on the left side. And on the right side, you already have a 2. So how do you complete that? It's going to be 115. On the left side, you have 294. And on the right side, you already have 4. So what number is going to give us 294? 290 is going to give us that. And how to identify this mystery particle? It's element 115. So we're going to go to our reference table and look for 115. And 115 is right here. So it's UUP. So we're going to write UUP. And we're done. That's it. So I hope you're going through these in order with me. And if you are, I hope you're getting better and faster at solving these, right? So I hope this was helpful. Thank you for watching.